presentation in the previous project. Let me first introduce my group members. Salib, Mustafa Shaib, Shadi Zirgis, and Rima Wali, and myself, Amira Yusuf. Our thesis project is about designing the Ponte dell'Alamaio, or designing the Alamaio Bridge. The outline of today's presentation will have a general introduction about the bridge, and then the technical bridge description of the existing bridge, design materials, work methodology, concept design, and our timeline schedule throughout the semesters, and finally the Alamaio Bridge is located in Seville, Spain, and is crossing the Guadalquivir River. Its function to transport vehicles and pedestrians from Cartuja Island to the city of Seville, and the designing process started in 1988 and its finished construction in 1992, and it is built especially for an event called Universal Exposition, or Expo 92. The project team is the famous architect Santiago Calatrava, and the structure design company is the Intexa structural firm, and the contractor is Constructions Constructors. And I'm leaving now with Marcus Salim.
The existing bridge is a cable stayed bridge with a single cantilever spar. The total span is 252 meters, and the free span is 180 meters. The deck width is 32 meters, and it has a pylon. The vertical height is 142 meters. Besides satisfying the basic design criteria, which are the serviceability and the economic and the safety, we have to have two-way, three-lane roadway and one pedestrian lane in the middle of the bridge. It has to be cable stayed with a single pylon without back stays. The proposed materials are concrete for the pylon, lightweight concrete or steel for the deck, and for the cables, FRP or heightened size steel cables. And we have to satisfy the existing soil conditions.
Now, arriving to the scope of our work, we have to limit our work because due to time constraints and knowledge also, because it's a very complicated structure and we cannot do the entire design of the structure. So we will have some elements that we're going to design along the process. We have the superstructure and the substructure. The superstructure will begin with the design of the deck, and then the design of the pylon and the cables, and finally the design of the pylon. And for the substructure, we're hoping it's an optional due to the very constrained time we have right now. The design of the foundations, especially the one underneath the pylon, because it is loaded with very high values of moment and axial loads. And also we are choosing not only the load types, we are mainly concerned for now with the dead load, the live load, the effect of temperature, and the effect of settlement. And we're going to explore different load types in the future of this semester. And in order to be able to successfully design such a complicated structure, we have to adhere to some codes. We have the H2LR FD for identifying the different load cases and the application of these loads on the bridge. The ACI 318 is mainly used for the concrete design elements. And the PCI is also similar to the ACI, but it's mainly concerned with the pre-stressed concrete elements. And finally, the AISC, which is used for structural steel buildings. We propose several software which will aid us in analysis and the design of different elements, which are the SAP 2000. The PCA software is used mainly for analysis of sections of concrete with irregular shapes, and also extract uses a very high-tech technique called the fibrous analysis technique for also analysis on and design of different irregular concrete sections. Now for the methodology.
About the methodology, our methodology is going to be made of or composed of three phases: the conceptual design, the design development, and the final design. In the conceptual design, we are going to start with the initial modeling and setting the structural system in which we are going to decide the structural hierarchy. It means what the structural elements are going to carry what the others. In the second step, which is the initial dimensioning of structural elements, we are going to assume some reasonable values for the cross sections and the lengths of the structural elements to start the modeling. In the third step, we are going to determine the cases of loading In other words, we're gonna figure out after analyzing the system what are the governing cases of loading. In the design development phase, we are gonna determine the exact dimensions of the sections after finalizing the analysis, and and we are gonna run some advanced analysis techniques like using it's not advanced, but it will be more complicated, like using area elements for modeling the behavior rather than grillage or fishbone models. And also we are going to determine the final design stresses after the end of the design development phase. In the final design phase, we are going to use all what we have done in the two other phases and decide the reinforcement, the steel grade, maybe the welding type or of the steel sections, if any. And then we are going to proceed to the connections, calculations, in which we are going to take care of the anchorage, the bearing, and all of these concerns. And finally, we're going to produce the design drawings. Now, let me leave you with the conceptual design.
For the conceptual design, first of all, by selecting the piling system, we're concerned about two issues: the tension in the cables and the movement in the piling. But first of all, let me show you the cases we could have upon changing the angle of the piling. The first case, when the piling is vertical, which is the regular cable stay, the horizontal component of the resolution of the tension cable will produce a huge moment, and this is undesirable. The second case, when the piling is inclined inside, we will have shorter cables, and they will less sag, and they will have less tension. But unfortunately, we'll have a huge moment because of the transverse resolution of the tension cable and the transverse resolution of the all weight of the piling. And this structure is already unstable, so we will not consider it because to be stable, it will need the backstays, and backstays are out of our scope. The last case, which is our case, when the piling is inclined outside. As we can see here, that the two components will cancel each other, and we will have longer cables, and they will more sag, but the tension will require more tension, but the moment will be less. Actually, the moment produced at the base of the piling will counterbalance the weight of the deck. And actually, we'll carry a parametric study for the angle for the exact angle of the inclination. Then moving to the concept of the actual cross section, it's a steel hexagonal box cantilevering two steel gauges. But searching for more economic and lighter system, we proposed either a composite section of a concrete box in two steel girders, or a lightweight concrete typical box section. As for the time schedule, our research process will last up to the end of our project because we're dealing with new systems and new materials, so we'll never stop learning about it. And we still have 2 weeks for the literature review. And as for the report writing, we have allowed time for it to be able to apply any changes at the last minute. And for the analysis and the modeling, it will take from week 4 to week 10. And for the design, we prefer to be more detailed and accurate, so we divided the time according to the design elements. The deck will take about 2 weeks, and the cables 1 week, and for the piling 2 weeks, and for the foundations hopefully will take 2 weeks. And finally, for the drawings production, we will start 1 week before finalizing our analysis and modeling. And then for the references, we used a couple of books about cable stay bridges and some online resources. And thank you. Please continue.
Thank you for the presentation. I have a question about your input loading. Are we going to consider seismic loading?
Yeah, it's an option for us. I mean, we're going to work on the basic gravitational, the basic gravity loads, and then we're going to include them in the seismic load design.
It's my belief that the wind load, at least, is an essential component of this design. So you cannot design this bridge only for gravity.
If you have enough time.
Yeah, the wind, I believe the wind should be an integral element of your design, maybe the seismic, as time permits. And in your analysis for seismic, if you will get to that, think about the multiple support excitation as the other group indicated. Basically, when we have 2 banks of the river, you expect that the ground motion input one side could be slightly, maybe significantly different on the other side, so that could produce relative movement between the two sides. For the other group, they had 2 pylons, so this is very significant. For you, you have 1 pylon only, so the implication of multiple support excitation could be different in the analysis. So if you're going to include the seismic, at least conceptually address the effect of this element. The use of PCI and ACI in design. You've taken, I believe, some bridge design classes. So you use the Egyptian code or the
Yeah, we use the Egyptian.
so you will have to go through the learning process of all these new codes you're proposing.
I have a question here for the shape of the bridge. What's the advantage of having 1 pylon, for example? Why not plate girder? I mean, maybe you have to emphasize on this point.
Yeah, it was the architectural concept.
So,
The main purpose of this project was to emphasize that the input of the architect must have a significant impact on the design itself. Not just the structural engineer must satisfy his needs with using typical shapes of the design. Not only we must use a cable stayed with 2 pylons, why don't we have one single inclined pylon? And we must adapt our knowledge to this types of shapes and different designs.
so if we compare this design with conventional design, will it have any kind of advantage from the structural point of view? Just it is fulfilling the shape of the...
Not just for the architectural viewpoint, it must say both designs should be safe, at least, and durable for using. But it's mainly for the architectural purposes, because here we are developing a new sense of engineering that we must develop our visual landscapes in Egypt. So we must improve our design techniques in order to adapt to anything, in order to enhance our landscapes and bridges and these landmarks.
You are going to assume that the pylon is fixed from the bottom, or you are going to go through the design of the foundation?
Mainly we are discussing the design of one main foundation which is under the pylon, but through our research we found it's basically better to use it as a fixed foundation.
So you are not going to include this in your work? I mean, you are going to go through the design of foundation of the pylon?
Yeah.
Yes, the bias and the bias.
You are going to use the same soil properties?
Yeah,
Yes.
we have
You have
enough information around that. So we have a soil profile with the SPT numbers and the models for elasticity of each layer.
Just a small clarification. You mentioned quickly parametric study for the angle.
Yeah.
Would you explain what you want to do exactly?
Basically,
No. Just tell me verbally.
because the inclination angle of this pylon is 58 degrees with the horizontal, which is a very weird angle to be assumed. Why exactly 58 degrees?
Okay.
This and why this is the question we're trying to answer. Through the different, changing the different angle of inclination and studying the effect of stresses inside the pylon
And
especially.
redesigning the whole thing?
No, maybe if we found that the angle is better in usage for in terms of less stresses. Of course, yes. The main design scope.
Yeah, that's the architectural purpose.
But for the main scope, we are also designing the pylon. That's part of our scope. So maybe it may be changed, but the same shape, the same concept, the same inclination of the pylon and the same concept shape.
I have a clarification on this. As the angle changes, straining action on the deck changes. So the moment the axial forces change, because they are components of the cables, so there will be an optimization probably through the section design between the axial force and moment interaction on the deck. And basically that minimizes the cross-section.
And you estimate the volume of work in that part to be time consuming, or?
No, it shouldn't take long. This is a cross-section and design only on the
Because
software.
I got worried when I heard parametric study, I thought that would be a whole lot of work.
This is back section.
Yeah, I guess I can add one more thing, that there is an advantage in materials from the existing bridge and the bridge we're designing right now. It was made in it was constructed in 1992, and they used to use these strands in the cables. Nowadays we can use the FRP cables or the parallel wires and the cables, and this gives us an advantage in the tensile forces that we can induce in the cables, and this may change the number of the cables, their sizes, and this will change the whole thing about the angle.
So you're going to do the FRP cables?
Yes, maybe. We're going to investigate.
You're going to look into that?
Yes, we're going to look in between the parallel wires and the FRPs.
Is the hexagonal cross-section pretty typical for such?
Well, it's not, but I think it's very good for such a position, because the bridge is supported from its mid-width, so it has a good torsional resistance that other sections will not support.
So you're going to try the 3 cross-sections, basically?
Yes. Yeah, actually 2, because one of them is already existing, so we know that it's behavior.
Okay, thank you.